Welcome to this explainer. Have you ever stopped to think that just rolling out of bed in the morning is governed by the exact same math that launches rockets into space? It's wild, right? Today, we're going to break down the fundamental physics of motion. But don't worry, we're not staring at a dusty chalkboard. We're looking at exactly how these concepts work in your daily life. We're going to uncover the hidden physics behind how you walk, how you cycle, and how you commute every single day.
So here's our agenda for today. We're literally going to take a typical day and map it out. We'll cover rest and motion basics, distance, displacement and direction, speed, velocity and acceleration, uniform versus non-uniform motion, graphing your daily commute, and finally, equations and circular motion. Lots of cool ground to cover, so let's just jump right in.
Section 1. Rest and Motion Basics. Are you truly still? We start our days simply by waking up and getting out of bed, which is actually a perfect way to illustrate our very first concept.
So, let's establish the baseline of our physical world. In physics, you are at rest when you're not changing your position relative to your surroundings. Basically, when you're fast asleep in bed, your position relative to the walls of your room isn't changing. You're at rest. But the second that alarm goes off, even if you hit snooze a few times, you eventually throw off the covers and start walking toward the door. Your position is now changing over time. You are officially in motion. I know, it sounds super simple, but this idea of relative change in position, that's literally the absolute foundation of all physics.
Moving right along to Section 2. Distance, Displacement, and Direction. Mapping your path. As you step out your front door and start walking, well, things get a little bit more mathematically interesting.
Before we can really measure your morning walk to the bus stop or the coffee shop, we've got to establish the crucial difference between two types of measurements, scalar and vector quantities. A scalar quantity only has magnitude, which, honestly, is just a fancy science word for an amount or size. Think of the step counter on your phone or your smartwatch. It just calculates how many steps you took, totally ignoring where you actually went. That is a scalar measurement. But a vector quantity? That has magnitude and direction. It's much more like a digital compass app tracking exactly where you're heading. In physics, whether your direction matters changes absolutely everything about how we calculate your journey. To put this into perspective, imagine you're walking through your neighborhood. You take a left, maybe dodge a puddle, take a right around a park, and finally, you arrive at your destination. Your distance is a scalar quantity. It's the total, winding, physical path your feet actually walked. Think of it like what your car's odometer tracks. But your displacement, that's a vector. It only cares about the direct, straight line from your front door to your destination, plus the direction you went, exactly as a crow flies. So you might walk a total distance of 1,000 meters weaving through streets, but your actual displacement might only be 200 meters north.
Section 3. Speed, Velocity, and Acceleration. Pacing your commute. Now let's say you get into a car or hop on a bicycle for your commute, and you start picking up the pace.
Here is where it gets really interesting. When you're driving down the road, you look down at your dashboard, and you have to ask yourself a fundamental question. What is the actual difference between my speed and my velocity? People use these words interchangeably all the time in casual conversation, but in science, they mean very, very different things.
It turns out your car's speedometer is only telling you half the story. It only shows your speed, which is that scalar quantity we talked about. It tells you you're going 60 kilometers per hour, and that's it. But if you add a compass heading, let's say 60 kilometers per hour east, that number suddenly transforms into your velocity, which is a vector quantity. And this leads to a fascinating side effect. Think about this. If you're taking a curving highway on-ramp at exactly 60 kilometers an hour, your velocity is actually constantly shifting. Why? Because your compass heading is shifting as you turn. Changing your direction intrinsically changes your velocity, even if your speed is perfectly locked in. Let's see how this builds into your daily experience. As you merge onto the highway, you press the gas pedal, and you increase your velocity over time. That is positive acceleration. But when you spot a red light up ahead and hit the brakes, you're reducing your velocity. We commonly call that deceleration or negative acceleration. And the cool thing is, you feel these vectors in your body every single day. It's that invisible force pushing you back into your seat when you hit the gas, or the one making you spill your coffee forward when you hit the brakes. Your entire morning drive is really just a continuous, visceral loop of accelerating and decelerating.
Which brings us to Section 4. Uniform versus non-uniform motion. Steady versus stop and go. Let's zoom out and look at the overall flow of your journey, whether you're driving a car or pedaling a bike.
Think about the different parts of your drive. When you finally hit a wide open stretch of highway and set your cruise control, moving at a steady, unchanging speed in a straight line, you are experiencing uniform motion. It's smooth, it's predictable, and it's relaxing. But contrast that with earlier, when you were stuck right in the heart of town, hitting every single red light just as it turned yellow, aggressively braking for pedestrians, inching forward in gridlock, stopping and starting over and over. That is a classic, deeply frustrating example of non-uniform motion. Your speed was continuously fluctuating, which is exactly why your travel time was entirely unpredictable.
Now for Section 5, graphing your daily commute, visualizing travel. Let's switch to a different mode of transport, like taking the train, and see how all this motion builds into visual data. If you really want to grasp motion, you've got to be able to visualize it. If we plot the distance a train covers over a few hours on a distance time graph, we can instantly, visually grasp how fast it's progressing toward its destination. A steep upward line means the train is covering a whole lot of distance in a short amount of time. So when you look at that steep upward line, don't just see math. Picture yourself comfortably sitting on an express train, rapidly speeding past all that highway traffic. Conversely, a flat horizontal line means time is ticking by but no distance is being covered. That perfectly represents the moments your train is stopped at a station to let passengers on and off.
Similarly, if we translate that train ride into a velocity timetable, a very distinct story emerges. At the start of the time interval, the train is pulling out of the station. Its action is accelerating, so its velocity is increasing. In the middle of the journey, it's cruising across the countryside, and the velocity remains beautifully constant. Finally, at the end, as it approaches the terminal station, it's decelerating, meaning the velocity is actively decreasing. Graphing this data essentially turns invisible physics into a clear, readable narrative of your commute.
Finally, we reach Section 6, Equations and Circular Motion, the math of motion. You finally finished your workday, and now it's time for some recreation, like playing a game of cricket.
Picture a bowler's arm in a game of cricket. As they wind up for a pitch, they swing their arm in a large circle. This is a perfect, everyday, real-life application of uniform circular motion. And honestly, this is one of the coolest, most mind-bending concepts in physics, because it actively plays with the very definitions of speed and velocity we discussed earlier, pretty much turning them completely on their head.
Let's break this down. Think about the bowler's hand. It might be moving at a perfectly steady speed, right? But because their arm travels in an arc, the physical direction the ball is pointing shifts every single millisecond. Therefore, since velocity absolutely demands a constant direction to remain unchanged, the ball's velocity is constantly changing. It's this brilliant physics paradox right in the middle of a sports match. You are actually accelerating the object merely by changing its direction, even if your speed is totally locked in.
Now, all of these daily actions, from the arc of that cricket ball to the braking of the train, right down to your morning walk, can be perfectly calculated using the equations of motion. Think of these as the ultimate cheat codes to everyday reality. They beautifully connect time, velocity, acceleration, and displacement. By knowing just a couple of these variables, these equations literally allow you to predict the future. Whether you want to know exactly when a speeding train will arrive at a platform or exactly where a fielder needs to stand to catch that cricket ball, these formulas let us calculate reality with absolute, awe-inspiring precision.
As we wrap up this explainer, here are a few key takeaways to actively look out for in your daily life. First, always note the difference between scalar and vector quantities. Remember, direction matters. Second, observe how a change in direction means a constant change in velocity, even if your speed feels perfectly steady on a curving road. Third, practice visualizing your travels using distance and velocity graphs. They really reveal the hidden story of your motion. And finally, keep relating these concepts back to daily examples like walking, driving, or playing sports. It seriously makes the world around you so much more fascinating.
And I'll leave you with this one provocative thought to ponder as you go about your day. We started all this by defining rest as not changing position relative to your surroundings. But considering our planet is constantly spinning on its axis and hurtling through space in uniform circular motion, are you ever actually truly at rest? Thanks for joining me on this explainer, and keep questioning the motion of the world around you.